Thank you very much for coming. We are starting our new semester of NIA CFD Seminar series. Today we have our 81st seminar in this series, and speaker today is our own Nishikawa. Hiro and Ilyu working in recent years on development of a new third-order accurate scheme for node-centered codes, and topic of today's lecture is one important advancement in this area, so that make all terms that contribute to this third-order scheme consistent, and allows actually to have real benefits from using third-order scheme. So then from here, please take over.
Thank you, Boris. Thank you very much for coming. So this is a work, has actually a long history, funded by early research office in NASA and software development. This is a work done by myself and Ilyu, senior research scientist at NIA. I'd like to acknowledge also Boris for his helpful comments on this paper, which will be available soon. So this is going to be a story about invisible hand. Invisible hand is a word used by Adam Smith, the father of modern economics, or free market. He explains it is not from the benevolence of the butcher or the brewer or the baker that we expect our dinner, but from their regard to their own self-interest. And this self-interest will be led by an invisible hand to promote the interests of the society. So he says by pursuing his own interest, he frequently promotes that of society more effectively. And this is the basis of modern free market. You just pursue your self-interest, which automatically leads to the social benefits. And the individual should feel free to pursue. And of course, I'm talking about CFD. Do we have invisible hand in CFD? So some researchers work on to develop ultimate Riemann solver, ultimate artificial viscosity limiters gradient viscosity scheme, etc. And according to this invisible hand, the best algorithm is achieved by individually pursuing the best algorithm in each component. You don't care about other stuff, and you don't care about the whole society. You focus on yourself, and then everybody will benefit. Whether this is true or not, I don't know. Sometimes it's true and sometimes it's not. I'm interested to discuss here today is the invisible hand exist for third-order H-based scheme. And before I get to the source term, I'd like to explain what this third-order H-based scheme is. H-based scheme, typically second order, is a very popular discretization method used by NASA's facility, cradles and tetrahedral. If we look at this conservation law as an example, H-based discretization is defined by integrating this over the zero volume, and the solution is stored at the node. And that's a nodal line, not a set average. So if you expand this sum of the fluxes evaluated at the H midpoint, what you find as a leading term is a differential form of the equation, and then some truncation error. And the numerical flux is typically consists of this consistent flux average, and then some dissipation. And I'd like to emphasize here that the H-based scheme approximates the differential form in a conservative way. And typically, it is known that the H-based scheme is second-order accurate on triangular and tetrahedral grids, the simplex grids. And typically, you compute the gradient at each node and then linearly extrapolate the solution to the H midpoint. And then you have left and right states that compute the numerical flux. And the recent discovery by Katz and Sankara, they discovered that this H-based scheme achieves third order if you compute the gradient by quadratic fit. So that is exact for quadratic function. And also the flux are linearly extrapolated. The gradient of the flux can be computed by chain rule. So all we need is the quadratic list of gradients for the solution. So if we look at this, so we have a quadratic least square. So we can actually get a second derivative. So if you pursue the best extrapolation method, that will be quadratic. But if you do that, you will lose third-order accuracy. This has been demonstrated in this AIW paper for Navier-Stokes calculations. You have to stay linear. And also, I'd like to point out, by doing quadratic least square is not really a big additional computations. If you fit the polynomial over neighbors, and typically we use their neighbors also, you have normal equation, you can easily invert this. And now this is 9 by the number of nodes, the big rectangular matrix, correspond to these solutions. But we don't need these second derivatives in this algorithm. So we only store the first 3 rows. So if quadratic least square is possible with compact stencil, this is exactly the same as linear least squares. And second derivatives are not needed. This is very nice. But the story changes when we get to source center. And I'd like to distinguish from finite volume and H-based. These two are different methods. Finite volume can be second order or arbitrary elements if you evaluate the flux at the not H midpoint, but at the midpoint of each zero phase. This is second order, and this H-based scheme computes the numerical flux only at H midpoint. And this is second order only simplex elements, triangular and tetrahedral. And going to the third order, typically you need one more point to compute the flux at the phase. And then you need a quadratic extrapolation. Now you need a second derivative here. And here the solution is not a nodal value, it's a set average. On the other hand, the third order H-based scheme achieves third order accuracy with exactly the same quadrature and the same linear extrapolation. And this is a very economical scheme. Especially in 3D, you don't need to compute a numerical flux at every zero phase. There can be a lot of them. We only compute a flux per edge, and then with a single phase node. So if you're only looking at this quadrature, you can devise a lot of different high-order flux quadrature by Gaussian quadrature, for example. But it's not going to bring third-order accuracy. It's going to actually destroy our third-order accuracy.
Yes? So could you go back one more slide? So on the right side, what are the differences between the second order H-based and third order? You use the same linear extrapolation. So when you get second and when you get third?
That's the difference.
You use the quadratic least square for the bottom figure, and then you get third order.
Yeah. And the boundary, third order accuracy, it's been shown that this H-based scheme can achieve third order accuracy on linear elements like this. And the reason why this can achieve third order is that the residual is exact for quadratic functions, no matter what the geometry is. For some boundary conditions involving normal derivative, it has to be accurate. But like I said, this is different from finite volume. You are not integrating anything along this edge. If you can integrate flux along this edge with very high accuracy, but it doesn't do anything. It actually, you lose third order accuracy. And also you can use high order curved geometry, curved mesh. But then the H-based scheme, I don't know how to apply H-based scheme. So there is a special boundary quadrature formula that needed to achieve third order accuracy for this type of geometry. And we have 3 Euler results also. And if you apply this beyond conservation law, if you have diffusion scheme, you can develop diffusion scheme on your own, like third order, fourth order. But when combined, the accuracy reduces to second order. And there are successful diffusion schemes. One is the hyperbolic formulation, and then the Pincock and Katz, they also developed a third order diffusion scheme that can achieve third order operation diffusion. But it's not independently developed. You have to be very carefully develop this third order scheme for other terms. So not necessarily the best ones. You have to be, every component has to be designed very carefully. And then how, I'd like to discuss later when I get to source step. That's the next topic. That's the key. And the invisible hand, whether it exists or not, we will see. So source step, now we have S here. There can be reaction terms or method of manufacturing solution. Our primary target is unsteady. When you have an unsteady equation, you have time derivative, we take it to the right-hand side as a source term. Whether explicit or implicit, they can be treated as a source term. And they have to be discretized in space in order to preserve third-order accuracy. But if you only consider source term discretization, what would be the best scheme for this source term integration? That would be this point evaluation. Like I said at the beginning, this term approximates divergence f. So this should approximate simply x. And because this is a nodal scheme, at the node you have the value. So this is the best approximation. This is actually exact. If you expand this in Taylor series, you get nothing. You get only this term. So this is exact. But then, you completely lose third order accuracy. So something is missing here. And actually, Adam Smith knew it. That's the rules of government. He says, according to the system of natural liberty, the sovereign has only three duties to attend. The duty of protecting the society from the violence, destroying third order accuracy. The duty of establishing exact administration of justice. We need some set of rules to follow, right? And then we need to maintain this certain public order. So free market works best when protected by laws of justice. And the question for us is, what are the laws of justice for H-based third order scheme?
So the second order is violence.
No, destroying third order would be bad. Okay, so in case of there's no source term, divergence f equals 0. This is the special property of H-based scheme. This is the reason why this achieves third order accuracy. If you look at the regular grid, on which the stencil is exactly the same at every node, okay, and then you expand this in Taylor series, you find this divergence f, which is the term this approximates, and then second order error here. These qxs, qiy, these are second order operator multiplied by these geometric constants. The directed linear vector nx, ny, and h vector delta x delta y, and sum over the edges. So as you can see, the divergence f pops out. So by definition, the truncation error is obtained by substituting exact solution. So if you substitute exact solution, this will be 0 because divergence f is 0. And this is also 0. And that's why you are left with third order truncation error. And then on regular grids, we expect third order accuracy in the solution. But this is not enough, because when you go to irregular mesh, the numerical scheme is likely to generate low order error, like first order error. But H-based scheme doesn't. On irregular mesh, this second order error is not factored this nicely this way, but it doesn't generate first order error. And on irregular mesh, it is known that if you have truncation error second order, you can expect third order error. It's not always true, but you can expect. So either one of them alone does not guarantee third order accuracy on arbitrary simplex grids. So any additional term, source term or viscous term, must be discretized under these conditions in order to protect the third order accuracy. If you break any of these, you lose completely third order accuracy. So in the case of when we have a source term here, so the discretization should produce second order error in this form, so that when it's substitute exact solution, this divergence f minus s is 0, and this is also 0. If you use point source, like I said, there are no truncation errors, and that's why this second order error remains like this. And now divergence f is not 0. Divergence f is equal to x. So this term remains, and you lose third order accuracy. On irregular mesh, of course, the source discretization should not generate first order error. And satisfying these two conditions, now you can expect third order accuracy. And this is very important for unstable. So they must satisfy these two conditions, and the source quadrature, clearly, it must have a second order truncation error. That factors. And that's why the best source discretization doesn't work. And there are already a known formula Aaron Katz in 2011, he proposed, he derived this formula. So this is a sum over each edges around node J. And he defines two values, SL and SR. That's this interesting formula. It's not a simple Taylor expansion. It has a -1/2 and -1/8. And this operator is defined as a gradient dotted with the H vector. And this is a square, so this requires second derivatives. All the second derivatives, x, 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 y, and y, y. And this BJK is called partial volume. That's the dot product of the H vector and the directed area vector. So this requires second derivatives. And there is another approach that I proposed some time ago. I look at the differential equation, just the source term. If we can write source term as a divergence form, and then we can discretize this by H base T. And I found this the fluxes that can achieve this. And these fluxes are defined around the node J, local. And these are cubic polynomials. If you differentiate these two, just plug in here, you will find that there's a third order error committed. But third order error is okay because this is to be used for third order accuracy. And then later I found that noticed that we don't have to use both fluxes. We can use just one flux. This is called one component divergence form. This also creates third order errors, but this can also be used to generate source and discretization. So this is a symmetric form, and that's that one component form. And there is also a special divergence form. If your source term is curl-free, like a gradient of sum, and then the source term can be exactly represented as a divergence. And this is the flux. And this formulation doesn't require second derivative, but this is so special that the source term has to be curl-free, and it's not always true. But once this source term can be written as a divergence form, it is so straightforward to discretize it. Just apply the same algorithm as the conservation law, and you achieve compatibility condition. But there is a problem. When we work on unsteady 3D Navier stores in Fan 3D, we realize that this second derivatives can be a big computational problem. 3D unsteady Navier stores, we need 6 second derivatives for 5 variables, and they must be computed and stored at every back plane in the time integration. And that's a lot. So the objective of this work is to remove second derivatives completely from the source quadrature and develop third order unstructured method that does not require second derivatives at all.
What do you mean by every backplane? The ones that are required for constructing the derivatives?
Yeah, at every times of n minus 1 and minus 2. We need
so basically do a couple of backplanes.
Yeah, we need to keep in order to.
Not the whole history, but just the 2.
Yeah, that's all. So we set up a problem. We took Aaron Katz's general form here, SLSR, with partial one. And I defined this left and right with arbitrary coefficients. So A left multiplied by Sj, that's source term at J. And then B associated with the derivative at the gradient term at J. And the CL is associated with the second derivatives. And then same to the right neighbor K. And we want to determine these 6 coefficients to achieve third order accuracy. And we know exactly what to do. We need to look at these conditions. First, we Taylor expand this expression up to second order on arbitrary mesh, irregular. And we look at this first term. This should be the consistent term. So this average of AL and AR should be 1. And second condition is to eliminate first order error. This is the first order term. So we require this coefficient to be 0. So these conditions must be satisfied, but not enough. But on regular mesh, actually you see this term will vanish. So we don't really need this condition here. So we can impose one more condition for regular grids. The last condition is the compatibility. This was the this involves a lot of calculations. Taylor expansion on regular grids. This is in 2 dimensions. You can find there is no first order error, but here is the second order error. And it is remarkable, I find it remarkable to find the same form as the conservation law. So in order to achieve 3rd order accuracy, these 2 terms must be factored in the same way. So this term, this coefficient, and this coefficient, -1/24, must be the same. And then we end up with this second order truncation error that vanishes. So this is the compatibility condition that needs to be satisfied. And we can show in arbitrary dimension, that was 2 dimensions. But we did analysis on 3D tetrahedral grids. And we found that this compatibility condition can be written in terms of the dimension constant. So if d equals 1, this comes from the 1-dimensional scheme. And d equals 2, 2-dimensional on triangular grids. And d equals 3 for tetrahedral grids. So we have 3 conditions lined up. And then we have 6 unknowns. So this is an underdetermined problem. And there are infinitely many solutions. This was a surprise, actually. I thought this source term discretization is so special, and there are many, but there are infinitely many. And now we are ready to pursue our self-interest for source term. We are going to find the best for our purpose by adding 3 more conditions. So we'll have 6 equations, 6 unknowns, and the solution can be determined uniquely. The first one I tried was a symmetry condition. So if we ask, this formula gives the same coefficient for the node j and the neighbor, and then solve the 6 equations for 6 unknowns, and we found these solutions. And it was a bit of a surprise to find that when d equals 2, that this reduces to Katz's formula. But it means that Katz's formula works only on 2 dimensions. Because when d equals 1 or 3, we'll have a different formula. So the accuracy preserved in source term formula depends on the dimension. It's not the same. And then next thing I looked at was if I ask no contribution from the neighbor, so can we discretize a source term just using the value at node j and ask these 3 conditions, and then a solution is given. And it finds that you don't need a gradient at node j, but you need a second derivative. So it doesn't meet our purpose. So then I move on to this more economical form. So I specifically ask no second derivatives. The coefficients for the second derivative is 0. And then I just said AL equals 1. And then we found this solution. And now this doesn't require any second derivative, as shown here. You only need source term value and the gradient. And this formula is a very economical formula because you don't need second derivative, but this is not unique. There's something you can still do. There's a 1 to 3 parameter. Instead of specifying AL, we can specify something else. And I decided to specify this BR in order to generate a formula that does not depend on any derivative at the neighbor. And then we found this special formula. This is a unique formula that depends only on source term value at j and the gradient, and then the neighbor value. And we call it compact formula because if this gradient at the j can be computed over the compact stencil, this discretization has a very compact stencil, depending only on the neighbors, which sometimes is possible. But still, we need to compute the gradient of the source term at every node, of course. And this is a very special formula because this has a close connection to the formula on a regular mesh. So on a regular mesh, like I said, the first order error vanishes identically. So one condition is redundant. We can ask 4. So we ask no derivative condition, only Sj and Sk. And we find this solution here. And if you compare this with the compact formula that I showed in the previous slide, this AL is exactly the same, and the AR the same. The only difference is this BL. So On the regular mesh, you don't need any derivative. But if you go to irregular mesh, you need to add one more time based on the gradient. So we have a table of these formula, and our the purpose for unsteady 3D Navier stores, the most practical formula is this. So this is the one we've been using, and this is compact and economical, and also it contributes a larger diameter for the implicit scheme, the Jacobian implicit scheme. And on the boundary, just briefly. Typically, H-based scheme, when you compute the solution at the boundary, you know that you need some boundary flux contribution. All I want to say here in this slide is that you don't need anything for this source term. We can use this H-collapsing approach that we used to derive boundary flux formula for the conservation law. If you look at this boundary integration formula, and then you move this, apply to this interior stencil, but you move this node to this node J, and you end up with stencil on the boundary. And then what's interesting is this partial volume is a dot product of delta x and directed area. They all vanish for these two elements associated with the boundary. So basically, you loop over all the edges in the cell, in the grid, and you're done. There's no special, but the divergence formulation requires boundary flux. So there are some numerical results. In one dimension, we solve this advection equation with the source term. And here is the source term and the exact solution. And this is actually the exact solution, exponential function on the irregular mesh. 31 to 511 nodes. And this is the error convergence results. The red one are the new formats derived in this study. And the black is a point evaluation. This is an error in the interior nodes, and this is outflow boundary node. So the point formula, or regular formula, or Katz formula, you cannot achieve thorough accuracy. But with this accuracy preserving formula, all these formulas give thorough accuracy. The interior nodes, and also at the boundary node. So all new formula with d equals 1 is thorough accuracy. And in 2 dimensions, we tried this for a Burger's equation with source term. And here's the exact solution. The exact solution is always positive. So this top boundary and right boundary are outflow boundaries. And irregular mesh 33 to 257. This is not just nodal perturbation, but we use diagonal swapping to have a random number of neighbors at every node. And the results show, as expected, the point and the regular formula do not give thorough accuracy. The errors are very high. But divergence formulation of new formula, and including Katz now works in 2 dimensions.
For quadratic list, we use here neighbors of neighbors stencil?
This one, neighbors of neighbors, yeah. But for regular gradient results in the paper, we use only the neighbors. Yes. So also at the boundary, we achieve thorough accuracy. And thorough accuracy at the boundary is very important for this H-based scheme. This is outflow, so the error committed will not propagate back. But in general, that's not guaranteed. So we want to make sure that everywhere we achieve thorough accuracy. And here's an interesting example. I just wanted to show that consistent and vanishing first-order error is not enough to achieve thorough accuracy. Typically, if you have second-order truncation error, you would expect thorough accuracy in the solution on irregular mesh, but that's not always true. And in this case, we know clearly why. This formula, I call it F1, satisfies only 2 conditions. It doesn't satisfy the compatibility. But because it eliminates first-order error, the truncation error is actually second-order on this irregular mesh. This is a comparison between F1, this incompatible formula, and the compact formula. So both have second-order truncation error, but this is a discretization error, a blue one. This incompatible formula cannot achieve thorough accuracy in the solution. So the compatibility condition is necessary to achieve thorough discretization errors. And the same Burgers equation, but on a curved boundary, outflow boundary. In this case, again, on the left, we have interior nodes and right outflow boundary nodes. As expected, we, again, achieve third-order accuracy with the compatible formula. But point and regular, we don't achieve third-order. But on the boundary, this is an interesting case. This is divergence form without boundary closure. So in this case, it's completely loose, even second-order accuracy in the solution. But with boundary flux applied, and then it achieves third-order accuracy. But while doing this study, we wanted to investigate these details, but these details are not important anymore because we have a very economical formula and we don't need boundary flux, so life is much easier now. And we have 3D verification with Euler equations with manufactured solutions. The irregular grids, this is a curved cube, n by n by n, and it goes from 15 to 40 using manufactured solution. And we apply this, implement all these formula into FunCD to verify the accuracy. This is the accuracy of x velocity component. With the point quadrature, you get only second-order accuracy on the interior nodes and boundary nodes. But with this accuracy preserving all the formulas, you achieve third-order accuracy. And again, this divergence formulation needs boundary closure. And I guess the boundary closure is not implemented, right? Because we don't need to implement anymore. So conditions identified for third-order edge-based method. I think this is a big deal. There are two conditions: vanishing first-order error, compatibility condition on regular grids. Now, under these rules, now you can seek your self-interest, and invisible hand exists. Otherwise, it was very difficult before what to do, how to derive these formulas. So the family of source quadrature formula derived, and surprisingly, there are infinitely many formulas exist. And then we were able to pursue our self-interest for source channel and derive unique and practical formulas derived for, and that was the compact formula. And this is a great step towards low-cost third-order unstructured grids scheme for unsteady problems. Because now we don't have to compute and store those big second-order derivatives. And finally, whenever we talk about Adam Smith, we talk about John Nash. John Nash, I think it is famous enough, who was awarded Nobel Prize in 1994 for his contribution to the game theory. And his discovery was taking a famous example of prisoner's dilemma problem. If you seek your self-interest, I mean, if everybody seeks self-interest, you end up with an equilibrium. That's called Nash equilibrium. And he pointed out that's not optimal for the group. So he says the best for the group comes when everyone in the group does what's best for himself and the group. And this argument is often used to refute Adam Smith. And in CFD, if a researcher focuses on implicit scheme, he has a choice. Edge-based low-cost scheme, but it has to be compatible with other terms, or just see whatever the best for the implicit term. And it's likely that the truncation error will not have second-order error. That will cost more. And exactly the same story for the source or discrete scheme data. So you end up with this third-order scheme. Yes, you achieve third-order, but with high cost. And as Nash pointed out, here is a optimal or better outcome for the group. So the important implication I learned from this study is that more economical third-order scheme can be achieved when we cooperate and be compatible with each other. Thank you.
So